So we are very glad to have Professor Boris Zilber from the University of Oxford as the next speaker, and he's going to talk to us about model theory and finite universe. Please go ahead.
Okay, thank you very much. Right, so so this topic is something of I don't know, experimental science, if you want, but it is also something that I have come as a result of natural developments in model theory, and this natural developments that led me to think on structures from physics. It is not the other way around, and here you will have some of the conclusions and the intermediate sort of steps of research I'm going to present now. So there are a few things that can be read. It's some of this is published, and so this one below is the is quite detailed one. So, but the most detailed one is not in this list. It is you can see it on my webpage. Okay. Anyway, so so let me just introduce it into several ideas of mathematical logic and model theory of the way that we look at mathematics and broader on physics. So model theory studies mathematical structures in the context of certain formalism of the formal languages. Well, in principle, you can even think of languages of that one uses when communicating with computers. This is an example of formal language, and the more common type of mathematical formal language is the one that we use when we do when we write this conjunction, implication, and use quantifiers for all and there exist. That's basically what is meant by formal language. But to apply all these notions, you also have to choose when you define a structure. You have to choose the relations on the structures that you fix when you talk about the structure. So this would be speaking more technically, some predicate variables. Okay, so in such a formal language, when you have a concrete mathematical structure, you can then write down a description of the structure by writing down a list of every sentence, listing sentences that you believe are true in the structure. So if you write down the full list of such sentences, which is of course a little bit of abstraction. It is indeed an abstraction. What is the in general the complete list of sentences in the given language that describes your structure? So this would be theory of your structure. So this theory is completely formal. You can say a syntactical object in mathematical terms. So this is a picture that in more detail we see, and here I want to also emphasize that the structure for us consists of universe M and this L for a given structure M. It is very something important. This is in fact the collection of all the relations or predicates and operations that you fix when you speak about this given language, a given structure. So for example, when you speak about field, so if it is just field in the sense of algebra, then this L would contain addition, multiplication, maybe constant for naming 0, 1, this sort of things. So you see this as an example here. Oh, I see that maybe the option should have been a presentation rather than yeah. It is yeah. This is a better way. So this is what I just said about when M is a field. It will look like this, and this L is it would be called a ring language, and it is very important, this point, because often when you speak to a non-logical mathematician and you say the field of complex numbers, then people would imagine that wouldn't separate the other thing that they know about complex numbers, for example, metric, and well, topology that comes with this metric, and maybe the integration operations on complex numbers and so on. No, in model theory and logic, we are trying, and this is crucial, to be very precise about what we mean every time by saying that that's a structure of interest to us. Okay, now you see, now you can say that we look at a mathematical structure not as a as a non-logical mathematician just working with the structure with whatever content in whatever formalism of the structure. Usually mathematicians do not think too much about formalism. But when you approach a certain mathematical structure from a logical point of view, so you actually include an observer in this, because you really care about what properties of this structure can be observed in using the expressive power of the given language. So, as I just said in the previous slide, when we talk about sorry. So, when we talk about complex numbers, we we have to be very clear that we can observe polynomials, so we can observe the objects that can be expressed in terms of polynomials, namely curves, surfaces, algebraic curves, algebraic surfaces, and so on. But we cannot observe, for example, analytic curves and analytic surfaces. And that's very important feature of model theory. Okay, I just said this. In particular, well, first let's talk about actual infinite structures, and we can ask the question of how precisely can we determine or define the structure itself as such. So to be sure that we are in the given structure and not in anything else. And then in this case, the connection between the structure and its description, so its syntactic description would be like this. That not only we can, from the structure, construct our syntactic description, but also having this description, we can recover the structure. And indeed, this is a very essential property of the theory that we're building, thinking about the structure. And it is in the beginning of 20th century, there was an avid discussion in physics that's the notion of such a theory having this property. So this was called by the philosopher Joseph Petzold called univocal theory. And Einstein and Ehrenfest and quite a few of other physicists were discussing this for a while. And modern philosophers of physics also continue this discussion. So in model theory, there is a technical term for such. It is not univocal, but maybe a less fortunate way. We call it categorical theory. It has nothing to do with category theory, but the reason why it is called categorical is it means that what we say here in our sentences is so categorical that we can recover the so to say almost physically the structure itself. Okay. Now you see this notion of categorical theory is a crucial one in model theory. The reason why it is crucial, it's probably the same reasons why physicists were so much interested in it. You see, it is a natural property of any mathematical theory that you use definitions which are precise, that the definitions that so if the purpose of the definition is to define a concrete object, then the definition is as good as in the case it can really recover this object. So it is really sort of a leading property why mathematicians choose to deal with these notions rather than with that notions. And so in sort of philosophically, one can probably put forward this idea that the developments of mathematical notions and maybe even mathematical ideas is not just a chaotic natural evolution, but it is led by certain logical constraints, and some of these constraints, and maybe one of these most important constraints, is to be univocal in your definitions. Okay, so in model theory we have Rich theory that started with in 1966 with a crucial theorem by Michael Morley, and we didn't understand at that time that this is the beginning of some very rich theory, but it turned to be, and so it is it developed into something quite big. And the main conclusion of this theory is that if you add some mild assumptions, extra assumptions on the top of assuming that you deal with univocal theory, and the theory is rich enough, when we say rich enough, it mainly means that it is it is richer than just, say, linear algebra. It is almost the true right definition of what I mean here by rich enough. Then your univocal theory is really talking about complex geometry. But maybe it is when I say complex geometry, this complex geometry can in general turns out to be non-commutative. So this is this is a difficult and deep theorem that being worked out. But now it is very important remark here that complex, the fact that we deal with complex geometry is very essential here, and the formalism of the field of reals it cannot be part of this univocal theory. So the reals in this algebraic formalism is not included, cannot be included. But when you look closer at what this theorem says, and more interestingly, what are interesting examples of this sort of complex geometries that include non-commutative ones. And by the way, when proving this theorem, it is where we rediscovered the world of non-commutative geometries. You see, people who worked on this subject. We started by not knowing enough about geometry, and we rediscovered in the same way as probably the generation of Heisenberg and others discovered non-commutative geometry. Right. So this complex non-commutative geometries, they involve specific, potentially very large finite structures. So these finite structures are essentially, it's a very good example of this finite structure. It would be a finite version of the Heisenberg group. And it is a typical way of how you construct out of say complex planes, complex curves, something more interesting. You intertwine it with some combinatorial structures and get something more interesting. Right. So, and that's how we come to idea or to necessity of considering huge finite structures that might be part of our interesting of the world of interesting univocal theories. So there is a way of formalizing this notion of huge finite structures. So some people called it hyperfinite structures. In model theory, we more often usually call it pseudo-finite. It doesn't matter. And this notion is known since probably 1950s. Maybe some people knew it earlier. And let me give you this technical definition very quickly. So this structure N, which we expect to be infinite, we say that it is pseudo-finite if for any formal sentence phi in the fixed language that we work in, this language L, I mean, that for any such sentence, if the sentence hold in N, then there exists a finite structure that is a model of this sentence. So, in other words, any single statement can be any single statement about this pseudo-finite structure can be modeled in the world of finite. Another way of defining this pseudo-finite structure and indeed constructing pseudo-finite structure is through the construction of ultra products. So we have a sequence of finite structures, a family of finite structures, and on this family or on the set of indices of this family, we have an ultrafilter D. And so what ultrafilter is there for? It is just for the notion of saying what does it mean to say that for almost all indices, something does hold. So almost all means that this set of indices where it holds belong to this ultrafilter. Well, it is also a notion, of course, widely used in topology. And indeed, it is a little bit like topological notion, a notion of limit. So given this data, we can construct this ultra product of these finite structures along this ultrafilter. That's how we think about this. and this gives us an infinite, in general, infinite structure. And this construction guarantees that this property of the structure does hold. There is a theorem in this regard. It's called the Losch theorem. So this is a way of producing pseudo-finite structures, and this will allow us to talk about limit objects. So we say that this structure M, there is now another structure M. We go on with to a more complex notion. So this is a pseudo-finite structure, and this is a new to us structure, and there is a way of saying that this structure is a limit of this one, and this simply means so this this sign, limit sign, actually stands here for a homomorphism, like a formal homomorphism in universal algebra. But the equivalent way of presenting the same notion would be if we go back and think about this as a ultra product of finite structures, and then we will say that that the structure M is the limit of this sequence of finite structures along along this ultra filter D. And the reason why we care about this being a homomorphism means that the reason is that homomorphism preserve positively definable relations that typically we think about this sort of relations as equations. So in other words, if you have an equation that holds along this ultrafilter on all these ni's, then this equation would pass here to the target structure, but not the other way around. So if you have inequality, if you have that 2 points are different here, say 2 points are different when we take this ultra product, then it could become the same, they could become equal when we apply this homomorphism. It's a natural property of homomorphism that can happen. In this case, the good way of thinking about what happened with these 2 points is that the difference between them was infinitesimal. And so this difference disappeared when we passed here. Anyway, these are some technical notions, but they are quite important. And now speaking about examples, you see this notions for M actually works well when M is compact in some natural topology. And now if we look at examples and we want to, I already spoke 30-something minutes. Yes, and so if we speak on examples, we want to compactify them. So for fields, for example, we can approximate the complex numbers, but again, we cannot approximate the field of real numbers. And this is important, but we can do something to approximate the reals, but as a somewhat different structure. So here is a little bit technical slide. Let's spend a minute or two on this. So what is the statement here is that we can try to approximate the reals by residue rings. So this is, of course, the residue ring modulo M. And in residue ring, we have addition and multiplication. We have 0, 1, and we can produce 2, 3, and so on. But instead of just considering this as a ring, we consider a fancier structure with two separate universes. We simply look at the same, but think it in two different ways. So I would call it the left version and the right version. And now we can take a multiplication. So this have additions only, and the multiplication happens between them. So multiplication is just going from here to, we take a pair from here, and we get ourselves to this. Now, what is the difference with working with this structure? So this is there is a formal difference, and the formal difference is results in the fact that we cannot take a product of 3 elements, because the result of 2 elements would already be here, and we cannot apply our bilinear map to something that is in here. We can only imply it to the left one. So so it is quite similar to this, but it's actually weaker sort of structure. And that's the reason why I call it the weak ring structure. And the theorem, main theorem here is that we can approximate the reals, but not as a ring structure, but we can approximate it as a weak ring structure. And this weak ring structure on the reals would have, again, 2 universes. One is the reals with addition and whatever constants you want. And another one, we write multiplicatively. And it is unit circle that we write here multiplicatively. This is our, this is the left sort, this is the right sort. And the bilinear map between them is essentially this one. And so what is a statement here is that in fact it is the only way we can include the reals into our picture. So this is quite important. And in this way we stay within this sort of category of univocal theories, and now we have our reals to do some physics. Right. So now I come to quickly say about the conclusions. So if we apply this finite approximation to get the reals in this weak form, in fact, it is not such a weak structure. We can build over this structure in the formalism of this structure. We can build a quantum mechanics with quadratic Hamiltonians. It would include the language to speak about symplectic spaces with Hermitian line bundle, with connection, and all this stuff about the group of symplectomorphisms, and so on. And on this, we can now try to do an actual exercises in quantum mechanics. Now, what is included here? So first of all, of course, I said that we are restricted here so far. quadratic potential. And the typical example here would be to deal with, of course, with quantum harmonic oscillator. So if we simply take the time evolution operator, we can try and do this exercise to calculate this Feynman propagator. And it turns out it works just perfectly. It's so this calculation produces exactly what you need. In fact, instead of real numbers, you have to use not every real number is part of this model. It is you have to use such ones that make these rational numbers, but this sort of rational numbers are dense, so you can really approximate whatever real numbers appear here. So in fact, it is in full generality. And the calculation here uses something that this is a theory of Gauss sums. So nothing very fancy here, but what is really fancy that it works with an arbitrary choice of the coefficients here. So we can actually work with true values of h and sine and cosine and so on. Right. So another exercise in this spirit is that we can calculate the trace of time evolution operator for harmonic oscillator. And again, it gives us a right answer. Well, it's not quite a trivial exercise here. You see, of course, this result is broadly known, well known, but I emphasize that the methods I use are completely rigorous, and there is no tricks here with interpreting limits in some fancy way, which all these tricks with renormalizations and this sort of things that is typical for this part of physics. And the final one is an example of the calculating the path integral. So it becomes this sort of calculating this sort of sums, which are actually finite sums with these parameters that are given by our finite model. And all these parameters are in those residue, the parameters that come from these residue rings that you saw in these previous slides. You see, so this calculation gives us precise results, exactly as expected. And what is interesting, again, this doesn't require any renormalization. There is, while if you use the traditional methods in physics, what you have here, you have integrals here. And so you first calculate this sort of thing as an integral. Sorry, this maybe sort of thing as an integral, and then do integral, do limit with this sequence of integrals. In fact, you are doing two limits, one when calculating integral and then when applying the other limit. And this is where actually the need of renormalization comes. And the advantage of this finite model is that you do it directly, and very effectively it comes out with the correct answer all the time. Okay, so this is all about the calculation. Unfortunately, so far I cannot boast higher degree potentials. I cannot calculate this, but I'm still hopeful. Now, some interesting conclusions for physics. So the first is what is practically I said, that it is consistent that the space of quantum mechanics is actually huge finite structure. But another thing which is interesting is that you see the time evolution operator acts now on some finite structure, and it actually is not invertible, and for this reason, I mean, this is what the model, how this model is mathematically presented. And for this reason, it is the time is not reversible, and in fact, after huge but finite number of time intervals, the model have to collapse. That's a conclusion you have to come to if you accept this as your model. Okay, so this is end of my talk. Thank you very much.
Thank you very much for the wonderful talk, Professor Zilber. Are there any questions in the audience? Yes, Roland?
I have a naive question. Is there a connection with non-standard analysis?
Yes, yes, definitely there is. You see, it's model theory is full of non-standard analysis. It's interesting. Okay, every time when you talk about non-standard numbers, and if you consider alter product of numerical structures, you work with non-standard numbers. Mm-hmm. So, and what in fact I was working here. So if you look at this number, so m and lambda, so they are supposed to be huge finite numbers. So these are non-standard. We are working, in fact, in non-standard arithmetic. That's true. But the difference with non-standard analysis is that well, non-standard analysis is in the background, but the model, the choice of model, is that what is essential here, and the leading idea here is this this theory here that has nothing to do with non-standard analysis, or I would say it is it is something that yeah, it is what is model theory today.
Mm-hmm. Okay. So thank you. Yeah.
Thank you very much.
Do you think that I mean, the goal would be to have a rigorous Feynman path integral, and do you see that by combining your ideas or your theory and the approaches made in non-standard analysis, one could really define a Feynman path integral?
Yes, that's the idea. Yeah, that's what I'm trying to. You see, now I stopped my attempts for a couple of years. It is just not within my technical powers to do these things. But yeah, that's what somehow I believe should be the case. You see, for this quadratic quantum mechanics case, of course, I had no time to explain. There are so many details here that in some wonderful, mysterious way feel in their places.
Mm-hmm.
You see, there must be something behind this, why it works so nicely.
So, but basically, I guess what you do could be also applied to stochastic calculus. So
yes, yeah, that's also that I plan to do, but again, because of my technical restrictions of my own capabilities, I haven't. No, but if anyone would try to think in this direction, this would be wonderful.
Okay. Thank you.
Thank you very much.
Thank you for the question. Are there any other questions in the audience?
Also, quick question. Could I ask a quick question?
Yes.
Thank you very much, Boris, for that lovely talk and summary. I guess this question I may have asked you many times. So am I correct in understanding, for example, say quantum mechanics over the integers, wave functions of integers, that would be an example of a non-univocal theory?
Sorry, I only now found a way to put my video. Sorry. So could you please quickly repeat?
Yeah, sorry. So I was just saying, just to check my understandings, if I did quantum mechanics or wave functions over the integers, that would be a theory which is non-univocal.
Well, it would be this sort of limit theory. It's so it is. You see, if we choose to do if we choose a finite model, then the finite theory is univocal.
Oh, see.
You see, every finite it is. If you think about this, because everything is finite, you can define everything very, but it would be huge finite. You see. And that's why you have to apply some approximation procedure, some limiting procedure, and so you so out of potential infinity, you work with actual infinity. But in fact, you know what I've been suggesting is that there is actually underlying some finite structure that we tend to see as an actual infinity. But it is the right way, seems to be, to treat it as a potential infinity. So in other words, you know, the way of thinking about this huge finite structure. Of course, the question would become, so what is the size of it? And the answer would be, the size is not observable. You know, it is some huge number, and it is not observable. But certain properties of the size are observable. So, for example, in this model, you have to assume that this is divisible, this number, the size of this line, say, in one-dimensional model, is even, and it is divisible by 3, divisible by 5. So it is divisible by all sort of standard numbers, and it is important property that without which you lose symmetries. And this property is observable because you observe these symmetries.
Why was Einstein thinking of this? Because you mentioned Einstein.
Well, it is exactly because of this philosophical. He was very resisting this the thought that the theory might have different models. You know, so what is actual physical universe? I mean, the cosmos and all things, right? So you develop certain physical theories, and then someone tells you that well, maybe there is well, of course, now one plays with the theory of multiverse that there are, but you know, you can go there and check with Einstein's letters and. Yeah, I attended a couple of conferences in philosophy and physics that they put all this the discussion apart by you know who and what said and why.
Thank you.
Thank you much.
Very interesting. Is there another question? If not, let's thank Professor Boris Zilber for the wonderful talk. Thank you very much.